This is the Chemokinetics podcast on thermodynamics, where the internal energy of a molecule and its sources, such as vibrational, rotational, and electronic, will be discussed. Energy is seen when there is a change from one state to another. During a chemical reaction, the number of atoms does not change, and all the energy captured in an atom below the valence shell remains constant, basically. Only the bonding changes between atoms. To the combustion chemist, the energy difference between the products and the reactants of a chemical reaction is of primary importance. Combustion is the study of utilizing the energy of change from one set of molecules to another set of molecules. The two states of a chemical reaction is that of reactants and that of products. For example, in the complete combustion of methane, we have the reactants, methane and oxygen, and then we have the products, CO2 and water. There is more molecular energy in the reactant state 1 than in the product state 2, so there is heat release. This is the basis of combustion. To calculate the heat released from the first law of thermodynamics, we are only interested in the difference in the internal energy between the products and the reactants. We need not be concerned in the complex transitional states that occurred to get the bonding structure from the reactants to the bonding structure of the products. One of the sources of energy that a molecule has is translational energy. The concept of temperature is related to the velocities of a large number of molecules through statistical mechanics. Looking at the whole system, the whole set of molecules have velocities ranging from very slow to very fast in a statistical distribution. The higher the temperature, the average velocity increases, and the peak of the distribution shifts towards higher velocities, as is to be expected. Each molecule with a specific velocity has a specific amount of energy. This graph shows the energy distribution with respect to temperature. As the temperature increases, the probability of higher energy increases. Using Boltzmann statistics, the probability of a given velocity at a given temperature can be calculated. M is the mass of the molecule and K is a constant. At a given temperature, we can integrate over V to get the average velocity. Substituting this into the velocity-energy relationship, the average translational energy at a given temperature of a system of molecules can be computed. In addition to translational energy, the molecule itself contains an inherent energy. At the level of the chemical bond, a molecule is a complex object to model and its complex set of vibrational, rotational, and electronic states. However, these can be parameterized into simple quantities that capture the energy that is stored in these states. For example, the specific heat of a molecule parameterizes how much chemical energy that a molecule with respect to temperature. At higher temperatures, the molecule vibrates and rotates faster, for example. Just as translational energy is associated with a molecule moving through space, there is energy associated with the vibrational movement of a molecule relative to itself in space. The IR spectrum shows these vibrational modes. With each vibrational state, there is an energy associated with it. The methane molecule has two major modes associated with bending and the stretching of the hydrogen relative to the carbon. In addition to the vibrational states, there are energies associated with the rotation of the entire molecule. You can see that each vibrational state has rotational states associated with it. The figure also shows that the vibrational modes has more energy associated with it, i.e. it is harder to vibrate a molecule than it is to rotate it. Associated with even more energy is the excitement of the molecule to an electronically excited state. Within each electronic state, there is a set of vibrational and rotational states. Excited states play a role in combustion at high temperatures, and the transition state of a set of molecules between reactants and products.